Now we've probably got some idea of how the analysis of functions of vector functions can help us understand various types of complex motion. The functions we've looked at so far, the motions we've looked at so far, have been pretty complicated. So let's look at some tamer position functions. Okay, if we have the function r of t equals square root of ti plus 1 over tj, and we're going to restrict that to t values greater than or equal to 1. Main reason, or one reason being that 1 over t would not be defined for t equals 0, and square root of t would not be defined for negative values of t. We need to start someplace. We're going to start at 1. We could actually let t be greater than or equal to any value greater than 0, and restrict the domain accordingly. But this is the restriction we're going to use. We see that this function could be described parametrically by x of t equals square root of t and y of t equal 1 over t. We could sketch a graph of points on the path described by this vector as it moves through the plane, and we could, for example, have t values in the first column, x values in the second, y values in the third. When t equals 1, x equals 1, and y equals 1. When t equals 2, well, x is going to be the square root of 2, which is about 1.4, and y is going to be 1/2. By the time t gets to 4, x is going to be 2, and y is going to be 1/4. When t is 9, x is 3, and y is 1/9. It's not a very interesting curve, but let's put 1 here and compress the scale a little bit, and would have been nice to make that scale more even, but okay, if this is the point 1, 1, then that's going to be a point described by these parametric equations, and that's going to give us, that can be interpreted as a vector, r at t equals 1. So we have our vector r of 1. At the point t equals 2, x is the square root of 2, which is about 1.4, and y is going to be 1/2. That's going to put us at a point about here, projecting down to a little, almost halfway between 1 and 2, and half as high as the x equals 1 point. So this would be our r of 2 vector. For t equals 4, x equals 2, and y is 1/4. So that puts us here. And here's our vector r of 4 at the point x equals 2, y equals 1/4. We're going to get additional points. When t equals 9, x equals 3, y is 1/9. That would bring us out to a point about here. Not going to draw the r vector, but we see that we're following a path that appears to look something like this. So our position r of 9, I guess I will attempt to draw that vector, would be here. In between t equals 1 and t equals 2, in a time that might correspond to 1 minute, let's say, or 1 second, our position is going to go from here to here. Between r equals 2 and r equals 4, which is could be thought of as a 2-second interval, we go from here to here, not that much further than we went from here to here. So we're slowing down. And by the time we get to t equals 9, our r of 9 vector, isn't all that far from our R of 4 vector. Our R of 9 point isn't that far from our R of 4 point. But it takes, say, 5 seconds to get from here to here. So we can visualize a motion that starts out fast and slows down and follows this path.